Hello everyone, in this lecture we will see the representation of a stress. How can you represent a stress? So as discussed earlier, we know that a stress is a tensor quantity. If I am calling this as to be a tensor quantity, I can say that stress needs a plane in order to identify itself, right? So stress is basically a tensor quantity. So if you want to write the definition for this tensor, so you can write the definition for this tensor. You can write what is tensor. Your tensor is a mathematical object more generalized represented by an array of components that are functions of the coordinates of space. Okay, so this is the trivial standard definition for tensor. Now whenever you write tensor, you need to write something in their subscripts. So the first subscript represents phase, the second subscript represents direction. Example, so if you are writing some sigma, and you need to write something in their subscript. So two boxes I have made. Here tau, two boxes I have made. What has to be filled in these two boxes? Here I have shown x. What does it mean? If I am writing x and x, so the first x represents phase, the second one represents direction. Clear? Here also if you are writing tau xy or sigma xy, the first one represents phase, the second one represents direction. Now some people follow this xy convention, some people follow 1-2 convention. So don't get confused, both are same. So x-axis, this x-axis, this x direction is also represented with direction 1. Y direction or y-axis is also represented with 2. Z direction or z-axis also represented as 3. So if I write sigma xx, it basically means sigma 1, or if I write sigma 2, it basically means sigma yy. Okay, now as I told you that we represent sigma for normal stresses. We use tau for shear stresses. But there is no harm if you represent tau with sigma, because some people use this sigma and tau interchangeably, but actually it should happen that sigma should be basically used for normal and tau should be basically used for shear, but people use it interchangeably, so don't get confused. Moreover, we talked about tensile stress, and I told you this tensile stress is given as P by A, which is the normal force per unit area. So let us consider we have the normal load, which is tensile in nature. So this is a block, so load is pulling it. So the load value is 20 Newton, area is 2 mm square. So here you can write sigma is equal to P by A, 20 by 2 Newton per mm square. So this Newton per mm square has got a special name. So I will call this as to be MPa. What is MPa? You write here 1 megapascal is equal to 1 Newton per mm square. I'm telling the units here itself such that later on you don't have any problem. So if I say 1 GPa, it means 10 to the power of 3 Newton per mm square or MPa. These are the frequent units which are being used in strength of materials, and you know very well that is what is the relation between Pascal. What is 1 Pascal? It's 1 Newton per meter square. So likewise you can simply convert, but these are the two major units that you will need in the calculation of problems of strength of materials. Here the value has to be positive. Why? Because we are talking about the tensile stress. And compressive stress, see, we have got a block and there is some compressive load acting, which is of magnitude 20 Newton. Area, cross-sectional area is 2 mm square. So here you can write sigma is equal to P by A, which is 20 by 2, which is 10 Newton per mm square. I have given a negative sign intentionally because this represents compressive stress. Okay, so sign convention for tensile is clear. Sign convention for compressive is also clear. Tensile means positive, compressive means negative. Okay, so they have got a separate sign convention. Now moving to tangential stress or shear stress, they have got a separate sign convention, so don't get confused with tensile, compressive. So they belong to separate family. I showed you in the previous classification as well that they belong to the category of direct normal stresses. Okay, and this shear stress comes under tangential. So tangential is purely different from normal. So leave that and just focus here. So here we have shear stress, which is given as tau is equal to P by A. So here P is not your normal load. What is this P? P is your shear load. Though I have used the same alphabet for representation, but make sure this is not normal load. This is the shear load, the load which is being utilized in order to rub this body on the surface. Okay, so if you divide the shear load to that of the area, so which area? The area, the surface on which you are rubbing. So that particular area we are talking about. Here we are not talking about the normal area. Here we are talking about the tangential area. Okay, so tau is equal to P by A. Here also if you can put some values, you will get some result. Okay, now talking about the sign convention for this, remember this sign convention, class 5 algebra rule, that is plus plus plus, plus minus minus, minus plus minus, minus minus plus. Okay, the simple basic fundamental rule that you use when your x and y, that is two coordinates, it could be xy, it could be xz, it could be yz. Okay, anything it could be. So here I have taken xy, so here you just see for x, if it becomes positive and this also is positive, then your shear stress is considered to be positive. If x is positive, y is negative, I will consider this to be negative. What is this basically, x and y? I am talking here about the face and I am talking about this as the direction. Let's see an example out here. I have taken a box, two surfaces I have taken. One is the top surface, this is my top surface, and this is my bottom surface. Alright, now here if I show something like this, that means an arrow going towards the right hand side, what will I write? I will write tau. What is the face? Which face I am talking about? Face is y, face is here. As you can see that this is your top face, that is going up, and this is your bottom face, which is going down, right? So face you just identify in that manner. So which is the face? Y face is there. Which is the direction? In which direction you are moving? You are moving in x direction. Okay, so face is up, that means it's positive. Direction is towards right, that is positive. So both are positive, and hence we can consider that this kind of shear stress is a positive shear stress. Clear? Now see this one. Which is the face? Face is y, where? Negative side. So y face is negative. Which direction you are going? We are going towards negative x-axis. That means this is also negative. So negative negative is positive, and hence we can consider that this shear stress is also a positive stress. Another thing, your shear stress always acts in pairs. You write here a note. Shear stresses always exist in pairs. That is they are complementary. There are complementary shear stresses. There are complementary shear stresses. Okay, so if you consider this top one as the main shear stress, its complement will be the bottom one. If you consider the right hand side shear stress, its complementary will be the left hand side one. Okay, now here let's play something, and you have to identify what is the sign for that, whether we will consider that to be positive or whether we'll consider it to be negative. So let's see. if I consider the top plane again, but this time I'm showing the direction like this, and I'm taking the complementary part, of course the opposite side on the bottom. So what is the convention? How will you represent it? I will write first tau. Why? Because I know very well that is acting tangentially, so there is no question of sigma. This is not a normal, so obviously it's a shear. But what should be filled here and here? What should be filled here? What is the face? Which is the face? Which plane we are talking about? We are talking about the y plane. Why? Because this is cutting this y axis, right? So this is y face. Which direction I am going? I am going in z direction. Clear? Here if you talk about this shear stress, I will write tau. What is the plane or what is the face? Face is y. What is the direction? You are coming in z direction. As you can see here, this y is positive. That means you are going in top face, right? In which direction you are going? You are going in negative z direction. So this is negative. So this shear stress will be a negative shear stress. Clear? Here if you see, which plane or face you are there? You are in y face. That means bottom side. So this is negative. Which direction you are going? You are going towards z axis. That is positive z axis. So this is positive. So minus plus is minus. So this stress is negative. So here you conclude one more thing, that if your main shear stress is positive, your complementary will also be positive. If your main shear stress is negative, your complementary will also be negative. Okay, but the direction and the sign changes accordingly. If you switch the plane, if you switch the directions, your sign changes. Let's take an overview of bending stress. So let's say I have a body. There is some central axis. I will call this axis as neutral axis. So this axis is been given a special name called neutral axis. Okay, now if I bend this, obviously I need to apply some forces on both the sides. After bending, this will look like this. So due to this bending, there will be some curvature formed, right? So if we complete this circle, let's say if we complete this circle, obviously we will get some center point. So from that particular point to this line or this axis, if you join this line, so this radius, I will call this as to be my radius of curvature. Okay, so this is my neutral axis, and the distance between this, I will call this as to be my radius of curvature. Okay, now let's say you are interested to find what is the stress at point P, at this point. What will I do? I will take a very small strip at that particular point and at a distance of y from the neutral axis. So what I have done, I have taken a small strip at that particular point from the neutral axis, and this distance I will name this as small y. Okay, so what I have written here, I have written small y is the distance between the strip and the neutral axis. Okay, what is this? Is the relation that I told you to remember in the previous class. So remember it, sigma b by y is equal to m by I is equal to E by R. What is sigma b? Sigma b is your bending stress. What is small y? Small y is the distance between the strip and the neutral axis. Then this capital M is the moment of resistance or bending moment. This I is a moment of inertia about the neutral axis. R is the radius of curvature, and E is the modulus of elasticity. Y by R, we call this as to be bending strength. Here you don't have to worry from where these all relations came. We will explain this more in detail when we will enter into bending chapter, but for the time being, for your overall picture, you just need to remember this much. That's it. Another important thing you should remember, that along the neutral axis there is no tension, no compression. There is a tension on the top side, there is a compression in the bottom side. If you are bending in this manner, let's say if you are bending this body upwards, if you are bending this body upwards, then what will happen? It will look like this. Now if it looks like this, again you can say that there is no stress or there is no tension or compression along the neutral axis, but inwards I will have compression here and outwards I will have tension out here. So it depends in which side tension is there, in which side compression is there. It totally depends. And the last thing about bending is, if your bending is like this, that is making a very smiling face, I will call this bending as to be a sagging bending. Okay, and if your bending makes a very dull face or sorrow face, I will call this as to be my hogging. So there are different terminologies given, so you can remember sagging when it smiles and hogging when sorrow. Okay, let's take a quick overview of torsional stress as well. So as you can see, we have got a circular shaft and this is fixed at one end and I'm twisting it. So due to twist, what is happening, the point A gets shifted to point A dash, and let's say it makes an angle theta. So this is the relation followed for torsion. So tau by r is equal to T by J is equal to G theta by L. What is r? R is the radius of circular shaft, the radius of this circular shaft. What is T? T is the torque or torsional moment or twisting moment. What is J? J is the polar moment of inertia, that is the moment of inertia taken about this central axis. If I take the moment of inertia about this central axis, about this red line, I will call that moment of inertia to be polar moment of inertia. If you have a very good idea of moment of inertias, fine, well and good. If not, then we will study this separately, but for the time being you remember what are the notations called. G is called the shear modulus or modulus of rigidity, theta is the angle of twist, L is the length of the circular shaft. If you know all these parameters, you can apply these relations, and all relations of torsion are derived from here. So when we will enter into torsion chapter, we will study more in detail about this, but currently right now there is no need of studying more in detail. For the detailed analysis, you need certain concepts that we have not introduced yet. I just gave you an overall picture such that you should be familiar what are the things that is going to happen or come in the future lectures. Okay, so these were some important things that you need to keep in mind. See you in the next lecture. Till then, bye.